So, I'm gonna pull for some knowledge from some of the other ones, but basically what a sparse table does is it's one of the various data structures that's gonna let us solve a range query in either O of 1 time under some circumstances or log n time. So what I mean by solving a range query is if we look at this like array up here, um a lot of times what you're gonna have to do in problems is you're gonna have to like do something over a range. So in this case, you want to find the minimum value over a range. So let's say you want the minimum value from like index like 0 to 4, so from like this 2 to the 5, then you want to be able to quickly compute it and see that it's equal to 1. What we can naively do is obviously just write a for loop that goes from like your starting point to your ending point. But in a lot of problems where like you're gonna have to like do some sort of sliding window, or you're just gonna need to be able to compute this quickly, this isn't gonna be fast enough. So instead, we have all of these like various techniques that help us solve range queries in faster ways. So an example we did like a few weeks back was prefix sums, right? So if you think of what a prefix sum does, you just calculate your prefix sum array, and then you're able to compute in constant time what the sum over any range is, right? Another example would be segment tree. So segment tree can solve all kinds of different queries, sum, minimum, maximum value, but it's a little more complicated to implement, which is why I decided to do sparse table instead. If you don't know what segment tree is, it's not important, but I'm just trying to get into like the importance of like what using a fast range query is. So what we're gonna use the sparse table for is we're gonna be able to solve these different types of range queries in, like I said, either O of 1 time under certain conditions, or in all the other ones log n. So let's start with the first example of using sparse table to calculate the smallest value on any given range. So if this is our array, then essentially what we do with sparse table is we calculate the answer for every single power of 2 length segment. So this is actually like what our sparse table would be, this whole like two-dimensional block, and it's actually how you're going to represent it. And what we do for a sparse table is the width of our sparse table will equal the width of our array, and the height will be equal to log base 2 of the width of the array, because you need to store each power of 2 length answer. We're never going to have to go more than log base 2 of the width of our array. So if we go ahead and look into this first row of the sparse table, what this means is we're storing the answer for every segment of length 1 in our array. So right here, what this means is at index 0, what is the smallest value on the segment of length 1? Well, for all of these segments length 1, it's just going to be the value itself, right? There's really no segment, it's just an individual value, right? So at index 0, the smallest value is 2, at index 1, the smallest value is just 7, and then so on, right? It's just each value all on its own. So usually this is kind of like our like initialization, or kind of like our base case. So we're gonna pre-initialize all of the first rows to be equal to the value of the array itself. So now if we want to start initializing the other rows, um notice that every single power of 2 with the exception of 1 is 2 times the power of 2 before it, right? So for example, like 4 gets broken up into 2 and 2, or like 8 into like 4 and 4. So if we want to find the answer to what is the smallest value starting at index 0 of length 2, so this cell would reference this segment right here, right? And then this one starting at index 1 of length 2 would reference this index right here. So instead of writing a for loop to calculate it, we know that we can just take the previous row's answers to calculate this cell. So since since 2 is, wow, this eraser is really dirty. So since 2 can be broken up into 1 plus 1, we know that we can take the answer of length 1 from the uh from index 0, and then take the minimum of that and uh the segment of length 1 from the next cell over. So essentially what I'm saying is this cell is the minimum of these two right here, which will just be 2, right? And I think it's a little confusing for the second row, but it'll make more sense for the other two. So if we continue and we fill in this row next, we want the minimum segment, the minimum value starting at index 1 of length 2. So once again, that'll reference this 7 comma 4. So the minimum of 7 and 14 is 7, and then if I go on ahead and just do the rest of them, 14 and 1, 1, 1, 5, 9, 6, 3. And you'll notice this last one right here, there is no element after, therefore like we just don't fill it in. Um, we usually also do this to avoid like falling out of bounds and stuff. It's not really important to fill this value in because we won't be referencing it when we're using the sparse table to construct our answer. So now when we go ahead and form this third row right here, we need to find all the answers of length 4. So once again, 4 can be built up into solving a segment of length 2 and then taking the other segment of length 2, right? So instead of doing a for loop starting from 0 and going all the way into 3, what we can do is we can use the previous row, and we know that we need the minimum on I'll highlight it here. We need the minimum of these two and the minimum of these two, right? Well, we don't have to write a for loop. We can just directly take it from two cells, right? That would be this cell right here and this cell right here. Because by definition, what this cell is, right, is it's telling you the answer to a segment of length 2 starting from index 0, and this is the answer from uh, index 2 of length 2. So if we take the answer in this cell and this cell, we get the answer on this whole segment of length 4. Does that make sense? So instead of writing a for loop to loop through this, we actually only take the values from these two cells right here. So if we take the minimum between 2 and 1, we get 1. And then for this cell, if we take the minimum between did I fill this in right? Oh yeah, right there. So if we take the minimum to 7 and 1, we get 1, and then maybe I should have continued to fill this ahead of time, but this should be the whole third row. So does it make sense how the sparse table is being formed? Are we still
Yeah, it
good?
makes sense.
All right, and then if we do this last one real quick, we know that if we want to find the answer to a segment of length 8, we just take the two segments of length 4. So that would be starting from here and then starting from here. So it will be minimum of 1 and 5. So we'll just get 1. And then we actually have to do it for this one over here as well. So 1 and 3. So we just get 1. And then this will be our entire sparse table. So now that we have an answer to every single power of two segments, how do we use this to retrieve an answer, right? So in the case where I'm just gonna actually spray this. So in the case that we need to find the minimum on a segment that isn't a power of two, then how do we do it? Well, the first thing I'm gonna show you is the trick for how to use sparse table for things that are solvable in constant time. So in this example, in order to determine if you can use this trick to solve queries in O of one time, you need to observe if calculating overlapping segments matters or not. So let's say for example we want to take the minimum value between let's say 1 and 6, right? So min of index 1 through 6. So what we're gonna do is we're gonna take the biggest power of 2 that's still smaller than our range. So the number of elements in the range 1 comma 6 is 6 minus 1 plus 1, or there's just 6 elements. So the biggest power of 2 that would fit in this is 4, right? So we're gonna take the minimum between two ranges of length 4. And the ranges that we're gonna take is we're gonna take the one starting at index 1 going to length 4. So we would take this right here. So from 1 to 4. And then we would take the other one from the back. So we would go from the right and then go 4 over. So we would go like that. So now what happens is if we take the minimum between these two ranges, we have our answer. So what we would look up is min of index 1 length 4, which would be right here, so 1, and then min of index 3 length 4, which is also 1. So the answer would be 1 for the minimum on this segment. So does that make sense how you're taking the biggest power of 2 that still fits the range, and then you're taking that length starting from your left point, and then you're also finding the answer of that length from your right point. And the overlap doesn't matter for minimum because the one way you can think of it is like reusing 3 and 4 in these segments isn't going to influence your answer, because like if you have multiple 3s in an array, it's not going to change whether the minimum or maximum ends up being 3. Like it's the same as only having one 3, right? But in the case where you're using a sparse table to calculate the sum, you can't do that, right? Because if we took the sum using this trick of taking this segment and then this segment right here, we would end up double calculating this part right here, so it wouldn't actually work. So are we still good?
Yeah. So if we want to take the sum, then we would just use prefix sum. Or,
No, you can still use sparse table. In fact, I would actually just recommend using prefix sum. But the reason I do mention it is like sparse table is still able to solve sum, but only in log n time. So I'll just go over that example right now. So here's the next array. Like I said, the first row will always just be the array itself, so I haven't really bothered writing it. Just imagine that this first row is your array itself, right? So let's now that we understand how to fill in the sparse table, let's just go ahead and fill it in, right? So length 2 starting from index 0 will be the sum of these two. So it'll be 6. Index 1 of length 2 will be these two, so 7. And then sum of these two, 10, 12, 11, 7, 5, 13. And then for this one, we need the answers from the segments of length 2. So we would take each of these two right here. So this would be 16, and then these two. So 19, 21, 19, 16, 20. And then same thing for this one. We need length 4, or we need the length 4 segments. So I would take this one and this one. So 32 and then 39. So we're all good on how to build the sparse table, right? So so the way that you utilize sparse table to find the sum is the way you can think of like numbers, right? Is every single number can be represented in binary, right? So you can use powers of 2 to represent any single number, right? So where I'm going with this is no matter what length the the sum you're trying to find is, or like what length the segment like of the sum you want to find is, it doesn't matter if it's a power of 2 or not. We can just break it up into the powers of 2 that would make it. So let's pick like some like number like let's pick a length 6 segment, right? So let's say we want to take the sum over 1 to 6, right? So this is a length 6 segment, and it's starting from index 1. So we're going to work from here. So if we want to find the sum on this segment, we can we can take the biggest power of 2 that will uh that will fit into this. So currently it's 4, right? So we go ahead and take the answer of length 4 that that fits in the segment. So that would be this index right here, right? Because at index 3, if we take the answer of length 4, we get these last 4 elements. So we go ahead and get that in constant time by going to the cell that represents that, which would be this one right here, right? Because the third row represents the segments of length 4. So we add 19 to our answer. So answer equals 19. And then now we've already solved for the segment of length 4, so we can kind of sub-problem it, right? So we're now no longer working from the sum from 1 to 6. It turns into the sum from 1 to 2. So now we've gotten this part down. We need these two elements now, right? So now we take the next biggest power of 2 that fits in the segment, which is just 2. And now we go ahead and get the sum on that index. So you'll notice if we get this one right here of length 2, which would be this cell over here, we we now have in a single element the sum that represents the rest of the segment. So we go ahead and add 7 to our answer as well, which will give us 26, and that will give us the sum on the segment. So does that make sense? So you're basically taking the biggest power of 2, getting that sum segment in constant time, and then removing that length from your sum or from your segment, and you're kind of subprobleming it down. So the time complexity of this will be log n, because in the worst case where like you have some number that's 1 and just all ones in binary, so like 7 is 1 1
Like
1.
255 or something.
Yeah, exactly.
Oh,
You would have to break it down into like length like I don't know. You'd have to
so
do length 128 and then 64 and then 32 and then all that.
wait, so is there benefit to this compared to prefix sum?
Not really. The
Oh,
only
okay.
the only reason is I think it's like a pretty valuable like technique to be able to like utilize powers of twos to solve queries. So
Okay.
another this is a very popular like technique where you basically store every power of 2 answer to
Mm-hmm.
construct like the final answer. It's also used in Fenwick tree and segment tree and stuff like that. So I kind of have this big meme that like advanced algorithms is literally just like pre-processing an extra log n so that you can solve stuff faster. So knowing that like you can answer any like range using powers of twos will help you understand like Fenwick tree and segment tree as well. So I wouldn't like I said, I'd recommend just using prefix sums, but I already have
Mm-hmm.
a prefix sum problem on the website, and I just threw it in the contest again, so you can try to solve it with a sparse tree or sparse table. So that's all. Just to recap, there's basically two techniques that you can use to solve queries. You can either break it in to the power of 2 segments when when like you can't overlap them and get the same answer. So in that case, it would be the sum. But in the case where you can overlap them and get the same answer, such as like the minimum, like once again, these two segments are clearly overlapping. But if I take the answer of these two, I still get the same thing, right? It's not the case with sum. So if we can use this technique where we just take the biggest power of 2 and then combine two segments, it's solvable in O of 1 because we're only ever taking two segments, right? But over here, it's going to take log n because we're going to have to keep trying all of the powers of 2's. So another example of something that you can solve like using this technique right here is GCD, right? So if you're trying to find the GCD of like a bunch of numbers, like I don't know, like 2, 4, like 8, it'll just be 2. If you calculate the GCD of,
Oh.
if you have this pre-computed as 2 and this pre-computed as 2, then taking the GCD of this range will give you the same answer, right?
Oh,
So
okay.
you can use this trick with a GCD as well. And that's partially the reason why I wanted to do sparse table this week, because I solved
Mm-hmm.
a problem using sparse table for this.
So in
So
the actual coding, would you use like a 2D array or
exactly. Yeah, exactly.
okay.
So the first dimension is gonna be, or I mean, I guess it's just preference, right? But personally, my first dimension represents log base 2 of the size of the array, and then the second dimension will just represent the size of the array itself. It is worth noting that like you can just you can literally calculate what log base 2 of the size of the array is, but what people usually do is they just like put 30 and call it a day. And the reason
Oh,
for that is like
okay.
30 is more than big enough, right? So
Yeah.
that way you don't have to really compute it, and it doesn't really affect the runtime because you're only doing like so many extra operations, right? So
Mm-hmm.
that's it. That's yeah, if we don't have any questions, that's pretty much it. The only thing I would add in though is I prefer to use sparse table over like segment tree and stuff like that because the advantage is that it's very short. I think sparse table is a pretty like underrated data structure because people tend to use segment tree because it's used all the time, but segment tree is a little like complicated to implement and I always make like mistakes when I'm doing it. Whereas when you guys code this up, I think you'll notice that constructing the sparse tree is later, or the sparse table is literally like 6 lines of code. So it's a lot easier to get range query answers uh, constructing a sparse table instead of using a segment tree. The main difference between the two though is that sparse table doesn't support updates. So in a lot of problems, like you'll have an array and you'll have to compute the answer on a segment, but you might have an update in the array like sometime in the middle of all the operations, right? So in a segment tree you can handle that update. In a sparse table you can't because you've already made the table, right? If you update one element you have to reconstruct the entire sparse table again, so it's not worth it. So just keep in mind that you can only use sparse table if you're trying to answer range queries in a way that the original array is never changed.
Oh, okay, cool.
So yeah, that's it. I never share the code. I go over solutions after, or I like push them to my GitHub, and you can look at it that way. But the problems are up. I can get you in the group, and then give him a shot, and hit me up if you have any questions.
Yes,
So here
please.
goes the recording.